Yeah, thanks Gautam for inviting, and it's great to be here and nice to see that there are so many people for this talk. I thought this talk would be one of those fringe talks which only 3-4 people would be interested, but great to see the room is getting full. So what I'm going to talk about is look at largely efficiency issues when one is dealing with large scale graphs. And for me, the graphs are typically not necessarily the social network style graphs, but largely from the linked data community. So we will see what this linked data graphs, how they are different from social network graphs, and how big are these, and what are the some problems that you see while you are trying to deal with these graphs, and how we can go about solving it. And much of the work that may come later in the talk is clearly not just me alone who has worked on it. I just haven't listed all my collaborators, but we can talk about it. I can send you the papers if required. So first, I don't need to give an introduction about what a graph is, right? Everybody knows what a graph structure looks like. It's one of the most general way of representing information, right? One of the most flexible forms. But let's focus on what is a graph database. As compared to, you can look at actually any relational database as a graph database in some sense. So you have foreign keys which link one record to another. So no issues. So you can actually form a graph structure using these foreign key relationships. And within a tuple, between two values in the tuple, you can actually form a relationship because they are actually related. That's why they are called relational structures. So how is it different from a graph database which is getting more popular nowadays? The key difference is in the way the data gets accessed. Right? In relational databases, the focus is always on indexed access to some tuple. So you know this group of values are a relation. So I just want to access this entire group and then process it. On the other hand, in graph databases, the focus is more on, I'm currently on this particular value, tell me all the values that are related to it. It need not be through a single tuple relationship. It could be normalized, denormalized, across foreign keys. I really have no control on what kind of relationship I'm looking for, but I could traverse this relationships from a given node. So this is the key difference, and this, if you again put it back in the relational world, it can be seen as a huge number of joins that you need to perform, right? Which is not a fun task to do on relational databases. So you want to avoid these joins. On the other hand, this is the only mode of traversal access that you are allowed to do on graph databases. Although we will relax it a little later and say that we want to do both relational style as well as navigational style of access, but this is the main difference between standard databases and graph databases. So some of the examples of what kind of questions you could get on graph databases: find all friends of Gautam. So you know a node Gautam and you want to find all relationships, find out only those relationships which say it's friendship and locate the other end of. So this is one hop BFS with certain kind of restriction, right, from the graph world. You can actually look at little more complicated issues. So there is another node called Srikanta, and I want to find out all the connections, that not an individual single hop connections, but anyone who can be reached from Srikanta. So I want to contact him and probably send out resume to him and say, hey, please propagate it in your network. So you should know how valuable that person is in terms of how many people he can reach out to, right? So look at Srikanta and look at all the reachable nodes from there, right? These are some of the queries which you don't often find on relational databases, but these are extremely common when we are dealing with graph databases.
Essentially, they're recursive joins.
They're recursive joins.
Including self joins,
yeah.
circles, everything.
Right. So recursive join is one way of looking at if you have self join, but it could be simply join, stream of joins. Okay. So it could be on the same table or across tables. You really don't have a requirement to stop that. So it's not again something very new. In fact, I haven't put the dates, but you can easily guess logic databases was well before, I think probably 80% of this room was even born, right? People have been working on it, and if you have met Alman or whoever visited TCS, you can easily see that these guys, yeah, they worked on Datalog, and even before that there was Prolog, which was from the AI side, and these things were 30 years long history, right? So that's where the real grounds of graph databases were sown, right? And then of course once the web came, it's very natural to see the web as a big graph, and you're all familiar with PageRank and Google's mode of trying to rank pages, which is largely a graph query, right, as we will see soon. And then XML wave hit database community, and XML is both a tree and, if you relax it a little, graph, right? So again, huge amount of work was came out during XML activity, right? I mean XML database research. So whenever you look at many graph papers from about 10 to 15 years old, then you will see they all refer back to XML, XQuery, XPath kind of settings. So although they are not strictly graphs, graph database research flourished during that time. But now there is even bigger beast called linked data, okay, which is what I'm really excited about, which I'm going to talk about in this talk. There, the linked data graphs are really graphs, as in XML was mostly tree structured with some deviations from the tree, but linked data is mostly graph structures with very little deviating from the graph structure, as in moving into the tree, very little. But so we are really seeing true graph requirements in databases now. So just to give a brief introduction of what these graphs would look like in linked data setting, right? So I just was thinking about which are the good examples to give, and then I happened to catch the DVD of Expendables, so I thought I will talk about the good old Bruce Willis and Dolph Lundgren, who are heroes in this movie, right? So you can form such a graph where Bruce Willis is one node and Dolph Lundgren, and you can have relationships like both were born in different cities, Idar Oberstein and Stockholm, and then both of them have worked in one single movie, The Expendables, and it's a movie, and you can even construct further relationships like this is a movie made in Hollywood and it's an action movie and these kind of things, and both of them are action heroes, out of which Dolph knows martial arts while Bruce Willis knows how to handle a gun, right? So this is a big, this is a small snapshot of a fairly large graph that you can construct just from IMDb dataset, just from movies that are out there. Yeah?
This looks like very similar to Google Knowledge Graph.
Yes.
That they created by using info from Wikipedia and first 2-3 sentences of Wikipedia.
Yes. In fact, Google Knowledge Graph is another RDF linked data graph that you can see. And in fact, they have used not just Wikipedia, they have used IMDb as well. They have used many of these almost structured sources in order to extract. So I'm not going to talk about much on how exactly they built the graph, but this is exactly what you're saying. This is the way Google Knowledge Graph also looks like.
But the problem with Google Knowledge Graph is they relate each node with some static nodes. They cannot operate on dynamically changing events. So if the query is related to dynamically changing events or some time series kind of data sets related,
Yeah.
then they clearly means
They have a problem using the knowledge graph directly. You are perfectly right. In fact, this is actually an active research area. I'm not going to talk much about it, but we can discuss this offline. In fact, this is also one of my research areas, coincidentally. So looking at how these event kind of data stream that is coming in, how you can represent them as graphs, how you can query them, and clearly the problems only compound from what I'm talking about here, right? So they're much harder problems. Google is still catching up with us on that front.
Just one.
Yeah.
Well, look at RTF. A predicate in one sentence can be either a subject or object.
Mhm.
And that makes the structure a little more complicated than a conventional graph. So, are we going to touch upon?
So given such a graph that you have constructed from known facts, right? So you can actually look at the graph as simply a bag of edges. So you can allow for multiple edges between nodes, right? This with the same label also, it's perfectly okay. RDF does not prevent it. So, and every edge is represented as a triple, which essentially says what is the source of the edge, what is the target of the edge, and what is the label on the edge. And edges are always directed in RDF setting. And again, in the semantic web definition, when you look at it, so RDF graphs, every node on edge has a unique identifier in the form of URI, but it's only a minor detail which is not really important for looking at RDF data as a graph, right? It just gives you some way of identifying the nodes and edges.